Hey everyone, welcome to Science in Perspective. In this episode, I'm going to take a look at a paper by Laszlo Erdos and Volodymyr Ryabov. Apologies for the pronunciation if it's a little bit off, but they provide a rigorous mathematical proof of the threshold that exists, you could say, between things that are localized and things that are delocalized in systems. Okay, so the paper itself is called The Zigzag Strategy for Random Band Matrices, again by Erdos and Ryabov. And so it sounds pretty esoteric, and I guess it is because it's coming essentially from pure mathematics, but it speaks to something that is more relevant to science and technology writ large, and even just to life, the way that we see patterns, thresholds and patterns kind of emerge. So I'll get all into that. Now, what this paper is doing is looking at, it's using a tool, you could say, called random matrix theory. And I'll give a bit of a background into random matrix theory so you can get a sense of how they modeled this. But really, in layman terms, what this kind of result is saying is it's a proof that once a system has enough connectivity, that whatever might have been confined or localized for various reasons I'll get into, start to actually spread out. And they start to kind of sample the full space equally. Okay, and you can kind of think of this as, I think a good example would be something like a superconductor, right? So a superconductor, and I've talked about that in another context a few episodes back, is, obviously going to be a material that allows the flow of electrons to happen without any friction, right? Basically frictionless, perfect conductivity, okay? And there's all kinds of applications for that. So we can think of a superconductor being able to do what it does because its electrons can spread out uniformly, or they can spread out very well. They can delocalize. So they don't form pockets. They don't get trapped, right? They spread out. If you have things like impurities or defects in your material, or even, let's say, the thermal agitation of the atoms itself, that tends to get in the way of electrons just moving as freely as they would like to. So those electrons would kind of get trapped. So that's why room temperature superconductors are basically non-existent, but are being worked on, because the regular room temperature is going to agitate atoms, and it's not going to allow electrons to just spread out completely freely. That's why you have to lower the temperature of materials to such a great degree, let's say using liquid nitrogen to stop the thermal agitation, and use super pure materials that don't have impurities or other defects in there in order to allow the electrons to just really spread out. Okay, so you can imagine there being a threshold where, something is, let's say, an insulator where the electrons are basically completely trapped and they can't move anywhere, barely at all. A semiconductor where they start to spread out, right? And they got some connectivity to them. And then a conductor where they're spread out quite well, then a superconductor where they have complete delocalization. So that the thresholds kind of between those have been interesting to physicists, to scientists for a long time, obviously materials scientists. And this paper is basically giving a mathematical proof that shows that, this threshold really does exist. It's a thing. It's not just kind of some general observation that we're making experimentally. Like, you can show mathematically that you can go from localized systems to delocalized systems, and what kind of controls the localized to the delocalized, where you spread out, is the number of connections in the system, the connectivity. So how many neighbors, let's say, any given atom in a system is talking to, right? The more they're correlated, the more connectivity you have in a system, the more things can spread out, and they showed that mathematically. So connectivity in systems delocalize things, allows them to spread out. So I'm going to argue, so that is a type of resilience, first of all, okay? Because you can think of delocalization as a type of resilience against noise, or against agitation, or against defects, a type of resilience against randomness, even, if you want to think of it like that, right? So imagine you were trying to make a superconductor and you wanted to raise the temperature at which it could exist, like closer to room temperature. That would be a very resilient material that would be able to maintain its delocalized, spread out behavior despite thermal agitation, despite maybe the incoming perturbations from impurities and defects or whatever else, right? So it is a material, or a system has a type of resilience to it if it can maintain its delocalization. Okay, but there's another type of resilience that systems have that's actually a bit more similar to localization, and that's pattern formation, right? So you can imagine, any system, the human brain, right, artificial intelligence systems, anything in biology, where the resilience that we typically talk about are, systems that take on non-random behavior. They have some type of pattern to them, and it's that pattern that's resilient. But that pattern is kind of the opposite of delocalization, if you think about it, right? Because now those patterns are more fixed. They're not just random. They're not just completely spread out. They don't just dissipate, to the whim of the second law of thermodynamics, right? It's not just nothing but entropy increasing. You have these pockets of lower entropy patterns, these non-random patterns that we observe in nature that we call life. And of course, you get this in other systems that aren't alive as well. Really, anything interesting has some type of pattern to it. And that's a type of resilience. So you've got this interesting, the paper is showing one type of resilience that you get through delocalization, where things can spread out, and like in superconducting materials, let's say. And there's also kind of statistical versions of that, maybe, informationally, when things can become more delocalized. You'd probably call it something like decentralized, right? Think of the internet, think about information systems. Decentralization could be very good. It's a type of robustness, right? It's a type of resilience to be able to decentralize, right? You get better fault tolerance, all that kind of stuff from an engineering standpoint. But then you've got this other type of resilience, which is the patterns that actually matter. So what is that? Because it kind of seems like they're opposites of each other. So I'm going to argue in this episode that there's a universal pattern here seen across all real-world systems, that you've got these two types of resilience at play, and they have to go hand in hand. They're not, even if you think of them as opposites, they both have to be there. You have to have the delocalization in systems that work well, regardless of how, what it is we're talking about. Delocalization is almost always critical in some sense, but you also have to have that low entropy localization in order for there to be meaningful patterns. And these have to work together. They both actually depend on each other. So first I'm going to give, as I alluded at the beginning to the paper, right, by Erdos and Ryabov, that they give this rigorous mathematical proof of this threshold, let's say, between a localized system and a delocalized system. And they show that if you increase the connectivity of the system, you get better spreading out, you get better delocalization, and it's a real thing, and they mathematically show where the threshold exists. But they're not doing it in natural systems. Obviously, they're just doing it using mathematical tools, and the mathematical tool they're using is a random matrix, or kind of more to the point, random matrix theory, right? So let's do a little bit of background on random matrix theory so you understand what this tool is and what it means, and then why a formal proof in mathematics might actually be kind of interesting as I get into the more real-world relevance of it, and then the argument that I'll be making that you actually need these two types of resilience. One, the type that is in this paper, and two, this type of pattern formation that you would see in real-world, especially living systems. Okay, so random matrix theory, what is that? Mathematical tool. Start with matrices, right? A matrix is basically just a table of numbers. Most of you probably know that. You've seen them. Maybe you've taken a linear algebra class. It's useful to model phenomena as tables of numbers. One, it's easy to look at. It's like an Excel spreadsheet. Like people just immediately get a sense of that they're organizing the world when things are in a table, right? You've got rows, you've got columns, and every row column entry is a unique value. And now I have a handle on all the values I'm doing, right? In science, you're measuring random variables all the time. These values, they're random because they're subject to chance. They almost never have the same value the second time you go to measure it, right? There's always a probability of values, right? So they're subject to chance. That's why we call them random variables. But you're measuring those, and it's good to put those numbers into a table. There's all kinds of things. You can transform them, you can invert them, you can mix and match them, you can do all kinds of things with matrices. They're at the heart of artificial intelligence technology. It's how we put values into large computational systems and GPUs and all that kind of stuff. So anyways, matrices are super useful. They're just tables of numbers. A random matrix is where we're putting random values, the random variables that we're measuring. We put those into the matrix because they take on scientific relevance when you do stuff like that. Because again, we're always looking at measuring random variables, you could say, right? Now, this paper takes a random matrix, and does a kind of version of it, which is called a band matrix. A band matrix is you've got your table of numbers, but they're almost all zero, except the diagonal, okay? And then what they do is they start to add values above and below the diagonal. Now, why is that relevant? Why would you look at a band matrix? Well, remember I said this table is trying to look at the connectivity in systems, like how many atoms are connected to other atoms, or how many people are connected to other people, or how many ants are interacting with other ants. Doesn't matter what the system is, right? Superconductor, we could talk about atoms. How much are those atoms correlated to each other? How much connectivity do you have? Well, it kind of makes sense, right? To take the values above and below the diagonal as a way to model connectivity. Because if you think about it, if you don't have any values above and below the diagonal, you only have the diagonal. Again, that's a matrix. It's a table of numbers. You have rows. You have columns. They're all zero except the ones that go along that diagonal, right? Well, the diagonal is where the rows and columns match up, right? So it's kind of like if those were atoms in a system, it would be like the atoms are only talking to themselves, right? Because it's just the row and columns. I hope that makes sense. They all just kind of match up with each other. You're not saying that any one of those values are talking to values outside of itself, right? If you put that into a table, you get a diagonal going along the line. If you start to put super and sub values to that diagonal, above and below, then that's the same as saying, okay, the points in that system, atoms, whatever, people, ants, are now, they have neighbors that they're connected to in some sense, right? It might be people talking to each other, right? It might be electron wave functions overlapping with other electron wave functions, right? Atomic orbitals, however you want to think about it. The more values you put above and below that diagonal, the more connectivity you have in your system. Okay, so this paper is modeling connectivity, right? The amount of connections in a system by using band matrices. And it makes sense to do that. At least that's one way you could do it, because the band, which is how thick you're making that diagonal, how many values above and below that diagonal, is literally how much connectivity you have in the system, right? Again, the diagonal is nobody's talking to anybody else. If I put values just above and just below that diagonal, things are starting to talk to each other. The more values I put above and below, the thicker that band is getting. Okay, so they actually are talking about the threshold of connectivity in this paper in terms of the thickness of that band, because that's how they're modeling connectivity in a system. Okay, so again, the paper's not talking about real systems, right? Directly anyway. In science you have to do a model, but they're really kind of esoterically just taking something from random matrix theory and saying we can define a system with a matrix. We can define a system that only talks to itself where there's no connections as a diagonal matrix, and then we can start introducing connectivity within the system using a band matrix, which is just values above and below. Sometimes those are called the off-diagonal values. Okay, so it all comes from random matrix theory. It's had a lot of success in looking at electronic transitions and all kinds of physical, nuclear energy levels and whatever, all kinds of stuff you can do with it. And actually, let's get into that a bit, because beyond just kind of saying, hey, there's connections in here, what you can do is you can look at the eigenvectors and the eigenvalues. So this is a very common thing to do. I'm not going to peel back all the layers. That's beyond the scope of this episode. But basically, if you take your matrix and you use it as an operator, which means it's going to take an action on some other mathematical entity, sometimes certain mathematical entities don't move much. Okay, so in other words, I take my matrix, I use it as what's called an operator, and it tells me how to basically, let's say, multiply values against this other thing, which might be a vector or something. And if I do that, if I keep multiplying numbers against this vector, and let's say that vector doesn't really change directions much. Maybe all the other vectors do, but there's certain vectors in the system that don't. Okay, we call that an eigenvector. It's invariant. Okay, typically the scale or it might kind of stretch, it might get kind of a transformation to it, but it won't change its direction. Okay, so just like I said, matrices can be used to model systems. Vectors are used to model systems all the time. And we're always interested in what those vectors are doing, and the direction of the vector is probably the most important thing you can look at when it comes to a vector, right? Its size is important, but its orientation in space, typically high-dimensional space, is super important. Think of, I think machine learning is a really good example of this. So in machine learning, we train these, which is the technology at the heart of AI. You take basically a big table of data, which has millions of rows and thousands, if not millions, of columns. And you could say each of those columns in that table can be represented as a vector in high-dimensional space. So typically, We think of space in 3 dimensions, right? X, Y, Z, but you can go beyond that as much as you want. You could have million, billion dimensional spaces. You can't visualize them, but you can mathematically define them. And we think of these vectors as playing out, like each column in that data set, as basically sitting somewhere in that high dimensional space pointing in a certain direction. And the way that that vector is pointing is what that piece of information means. Okay? If you change the direction of the vector, the information would now mean something different. Okay? And that's really at the heart of AI, right? You take a ton of data, you create a mathematical representation out of it in terms of vectors, and those vectors are all pointing in certain directions. And you can do things with those vectors, right? Depending on the angle between 2 vectors, that could maybe mean how different they are in meaning. You could tell which vectors are analogous to one another, right? At the heart of so much of the natural language processing and tools like ChatGPT, it's because of where vectors are basically pointing in high dimensional space. Okay, so the reason why I bring that up is that because the orientation of the vector is so important, if the vector orientation changes, the meaning changes. So when you're trying to do something in science, like define a really complex system and then try to figure what in that complex system has meaning, like what is kind of stable when everything else isn't, eigenvectors is a way to do that. Because again, these are the vectors that when you apply the big matrix to it, they don't really change, right? They don't change their orientation as much. So there's something non-random about them. There's something truly defining about the system, okay? If this vector is pointing here in high dimensional space and it means this, and I go to take my matrix and I operate on that vector and it flips and flops and goes everywhere, well, it doesn't mean anything, right? But if it's pointing a certain direction, I take my matrix, I operate on it, and it doesn't budge, even though maybe a million other vectors are budging, but this one's not. That particular vector is defining as a property of the system we're interested in, right? It's not just a random happenstance thing. I hope that makes sense. So that's why in linear algebra and random matrix theory, you'll use things like matrices and vectors. Now, I said you can use a matrix as an operator, but you can also use a random matrix as as an operator against the vector and find the eigenvectors. You can use a band matrix as an operator, right? Think of the matrix that you set up as trying to capture essentially the dynamics of the system. The values that you put in your table of numbers is trying to capture the dynamics or the behavior of the system. If it was complete, whatever that means, it would capture every possible dynamic the system could go through. Okay, you see this with in quantum mechanics and quantum chemistry. They'll use things like Hamiltonians, right? Schrodinger equation, all this kind of stuff, and they'll use matrices as operators that try to capture basically all the possible dynamics this quantum system can undergo. And then if you use it as an operator, you can look for eigenvectors, and those eigenvectors could be things like, eigenfunctions, which could be things like wave functions. It's a way of getting at the things that are actually there in the system as opposed to the randomness. Anyway, so random matrix theory, deal with matrices, deal with random matrices because we want random variables in there, deal with band matrices because you have this diagonal and then you have a thickness of the band which is capturing the connectivity of the system. And now they can look for things like eigenvectors and also eigenvalues, which are kind of the things you actually measure. And those eigenvalues can follow well-known statistics that you can be on the hunt for. I'm not going to get into all of it, right? But it's basically fill a matrix with values, apply it to vectors, see where the vectors don't budge. Now it's something real. The paper is kind of using this mathematical technique to figure out where these thresholds are between delocalization and localization. And they're finding that the more connectivity, the thicker the band, the more delocalization you get, the more resilient it is to being trapped or localized. Okay? So it's a way to model that. So again, that's one type of resilience. Now, so I haven't said anything about like thermal. I mentioned like agitation, thermal agitation, but I haven't really said anything thermodynamic for the most part, right? Because we're just talking about something in the system like a wave function can spread out if it's got more dimensions, if it's got more neighbors. More neighbors is kind of a way of thinking of dimensionality. Okay? I'll leave it at that. It's kind of beyond the scope, but it's a way to think about increasing the dimensions of the system, right? You've got more possibilities. You've got more pathways you can take. That's a resilience. But thermodynamics is inescapable. You have to deal with thermodynamics of systems too, even though this is just kind of like a formal proof in a esoteric pure math journal. You still have to, if it's going to have any relevance to the real world at all, you have to deal with thermodynamics, right? I mean, you could put that as the third pillar of science, really. You got quantum mechanics, you got general relativity, you got thermodynamics, right? You have to deal with it. So we've got this proof in random matrix theory from the paper that doesn't really have anything to do with thermodynamics, right? But the delocalized system, we're going to talk about eigenvectors. Those eigenvectors, those are the things that could spread uniformly as opposed to forming pockets. That's pretty akin to the equilibria that we see in thermodynamics, right? If you take a gas and you allow that gas to just kind of spread out uniformly, so every atom you could think of as visiting every possibility, well, that's kind of akin to delocalization, right? Things are spreading out. That's not what this math paper is necessarily alluding to, but that's inescapable, right? Thermodynamically, it's at least analogous, but even it's more than an analogy. Really, any system that you're looking at in the world is going to have a thermodynamic aspect to it, and it would have this spreading out. And so, what does that mean? Well, and I did this a few episodes ago where I was talking about microstates and entropy, and how you need to, if you look at emergence, if you look at emergent patterns, it's because you have so many different microstates that actually subsume to the high-level macroscopic thing that you measure. Go check out that episode. It's a few back if you haven't listened to that already. There's only so many right now, so you could listen to them all. But that's kind of this interesting connection, right? Like, if you think about it, you've got the second law of thermodynamics, which spreads a bunch of things out and tends towards maximum entropy. Entropy is always increasing. So you've got this kind of equilibrium that tends to establish where everything just spreads out. It's uniform. It's kind of like a uniform probability distribution. Everything kind of has the same value, the same likelihood of being in the same place, whatever, right? But we know that's not all you get. You also get these pockets of low entropy that form. And I argued that that's because when you do spread out and you do have a lot of different microstate possibilities, statistically, as a byproduct, you're expected to get patterns out of that. Because what you'll do is you'll have many, many different microstates that actually map to some higher level physical construct, right? A macroscopic property that you will measure, right? This particular pressure, this particular volume, this particular temperature, right? If I go to look at that system and that temperature is the most likely temperature that I measure, it's because it has the most possible different microstates that would produce that temperature statistically. So it means that when you get spreading out uniformity, you're creating a system that actually gives pockets of order, pockets of pattern. Okay, and I said at the beginning, that's another type of resilience, right? The patterns are resilient, but the spreading out is also resilient, right? The spreading out that the paper talks about is resilient to a lot of things that could stop things from spreading out, right? So if I have a gas and it's spreading out and filling the room, and it's at equilibrium, that equilibrium is actually quite stable. If I go to put another drop of gas in there, it'll shift the equilibrium, right? But in pretty short order, you will reestablish the equilibrium because things will spread out again. As long as you have enough dimensionality in the system, things will spread out. They will get uniform. And the second law of thermodynamics is driving towards that kind of uniformity. But because of that uniformity, you have the possibility for many microstates, which are the different configurations that the system can be in, to all produce the same temperature or pressure or volume or thing that we actually measure macroscopically. So you've kind of got this counterintuitive thing where the things that allow you to spread out uniformly are the things or the mechanism behind small pockets of pattern formation. And the pattern formation is another type of resilience. If you think about your human brain, right, the only reason you learn is because there are patterns that form that are resilient. It's not all just entropy. It's not all dissipated equilibria. Because if it was, you wouldn't have a single thought in your head, presumably, right? So you've got the resilience of pattern, but you've got the resilience needed by systems to make sure that they can spread out. Okay, the mathematical paper is talking about the spread out version, and I'm talking about the thermodynamic version where you actually get pattern formation. And so what I'm arguing is that the patterns that we see in science, technology, and life have these two faces of resilience, right? Statistically, wisdom of the crowds, you have a lot of connectivity. That would be like a larger band in your band matrix. A lot of connectivity, which is very spread out, kind of delocalized, but that doesn't produce uniform probability distributions. It actually forms probability distributions with peaks in it, because we get averages, right? A lot of times these are more fat-tailed than Gaussian, but you still get these kind of patterns that are forming. It converges, right? There's a convergence there to something that is stable, okay? So I think it's a cool example, to compare what the paper is showing by Erdos and Ryabov, that, if you increase the connectivity in a system, you're going to get more delocalization, more spreading out, and that's a type of resilience against noise. Again, think of the semiconductor, right? You're trying to heat it up, you're trying to agitate it, you're going to put defects in there. But if it's really resilient, it would keep delocalizing and keep conducting super well. Even just conductors, you could talk about that. But you have to balance that with the thermodynamic picture, which is that type of delocalization gives you another type of resilience, which is almost like the opposite of that delocalization, which is these pockets of pattern formation that happen. Okay, so I think you should expect to see that pattern everywhere in nature, and you do. And I think that's very universal. So that's it. That's it for this episode. I just wanted to show that it's good to think about the interplay between what are systems doing when they make a lot of connections to each other, right? More connections, you get more spread out, you get more decentralization. You see this in systems, internet, you see this with artificial intelligence, you see this in the human brain. But out of that delocalization, you get pockets of pattern formation, which have their own resilience, and these things have to work together. You need both. And I think there's a real lesson there, right? That, it's easy to pick one side over the other, right? You might favor a lot of strict logical structure, but now you're not dissipated enough to get the wisdom from the crowds. You're not sampling. You're not doing enough trial and error. You could be super, super duper creative and do a ton of trial and error, but you might find your life kind of dissipating and not anchored on anything that matters. Okay, it's not a stretched analogy. I think informationally, these things all converge to the same core universal pattern. There are two faces of resilience: science, technology, and life writ large. The one that spreads out and the one that converges. Okay, so that's it for this episode. Thanks everyone for tuning in. If you think you'd enjoy more of this type of content, become a premium member at either scienceinperspective.com or patreon.com/Sean McClure. Scienceinperspective.com is science-in-perspective.com. Patreon.com/Sean McClure as one word, SEANMCCLURE. And then just click on membership and you gain access to additional quality content. I teach techniques and mindsets that reinforce skills related to how to think like a scientist in everyday life. You can find those links in the description. Okay, just to go over that a bit, technique videos, you'll learn how to use tools and intellectual moves like scientists use in your everyday life. On the mindset videos, I talk about how to incorporate ways of thinking that scientists use, the attitudes, the mental habits, the interpretive lenses that make scientific reasoning powerful. That can be relevant if you're interested in science. It can be relevant for you to learn science more effectively and be able to recall it. And it can be just useful to learn these universal patterns and ways of thinking in your everyday life. So premium members get those techniques and mindset videos. They also get summary notes, transcripts, and visual concept summaries for every episode. You get a forum for asking questions. You get a Q&A and AMA session every once in a while with yours truly. All of that for just $9.99 a month. So again, you can find those links in the episode description. So thanks again, everyone, for listening. And for those of you who are watching, until next time, take care.